Hello, my name is Kane Reeves, and today we are going to be discussing the sign test as part of our final group project for Dr. Glover's elementary statistics class at UT Martin. We'll be using the following problem as we break down the sign test. The 4-H program leader for the Western region of Tennessee claims that the median number of 4-H participants in the yearly 4-H junior camp is not more than 120. The 4-H agent doubts the accuracy of this claim. The number of 4-Hers per year for 12 randomly selected years are below. At an alpha equaling 0.05, can the 4-H agent reject the regional program leader's claim? Here is the table we'll be using. It is called the critical value for the sign test. A non-parametric test is a hypothesis test that does not require any specific conditions concerning the population's parametrics. They are easy but usually less efficient than the parametric test. So the sign test is one of the easiest tests for non-parametric tests to be performed. It can be used to test the population's median against the hypothesized value k. The sign test for a population median can be left-tailed, right-tailed, or two-tailed. The null and alternative hypothesis for each type of test will be one of the following. Left-tail test, the null hypothesis says the median is greater than or equal to k, and the alternative hypothesis says the median is less than k. For the right-tail test, the null hypothesis says the median is less than or equal to k, and the alternative hypothesis is the median is greater than k. And the two-tailed test says the median is not equal to k, and the alternative hypothesis says the median is equal to k. Find the critical value. So, if the value is greater than the median, we're going to replace the value with a plus sign. If the value is less than the median, we're going to replace it with the minus sign. If it is equal to the median, we're going to replace it with a 0. And if the difference between the plus and the minus signs, it is likely that the median is different from the hypothesized value, and the null hypothesis should be replaced. The sample size is the total number of signs, which would be our plus or our minuses. If the sample is greater than 25, we're going to use the standard normal distribution, and we're going to get that from our table. Here's an equation that we can use. So now that we have all the information we need to know to work this problem out, we're going to go back to our example problem. So, the 4-H program leader for the Western region of Tennessee claims that the median number of 4-Hers participating in the yearly 4-H junior camp for Madison County is not more than 120. The 4-H agent doubts the accuracy of this claim. The number of 4-Hers per year for 12 randomly selected years are below. At alpha equals 0.05, can the 4-H agent reject the regional program leader's claim? So below are the 12 randomly selected years, or how many participants went each year. Now we're going to break down the information that we know, which should be the participation of the youth at the 4-H camp each year, which are randomly selected. The null hypothesis says the median is less than or equal to 120. This is a claim that was formed by the program leader. The alternative hypothesis says the median is greater than 120, which would make this a right-tailed test. And we're going to compare the data to the hypothesized median of 120. So if we go up to the top chart and we say 152 is less than 120, so we would put a plus sign. And then if we have anything equal to 120, we would put a 0, and anything less, we would make sure that we put our minus signs. So we know that we have 7 plus signs, 3 minus signs, and 2 zeros. So n equals 7 plus 3 equals 10. So n equals 10. We will disregard the zeros. This means that this is less than or equal to 25. The test statistics x is the smaller, so x equals 3. We're going to use this table to find out our value. So we're going to go down our left hand side here and we're going to find 10, which is n. And we're going to go back up to the top on the right hand side and find our 0.05, which is our alpha. And we'll go down and we'll pair it up and we should get our value is 1. So in conclusion, the critical value is 1. If the x is less than or equal to the critical value, then if we remember back our x is 3, then we can reject our null hypothesis. So the 4-H agent can reject the program leader's claim and conclude that the median number of 4-H's participating in the 4-H junior camp per year is more than 120.
This is a review of the Wilcoxon rank sum test. Let's first talk about what is the Wilcoxon rank sum test. Well, it is a non-parametric test that uses ranks to compare the distributions of two samples taken from populations. There are two major rules or assumptions to remember when using the Wilcoxon rank sum test. These are the assumptions. Number 1, the samples must be random and independent. Number 2, the size of each sample must be greater than or equal to 10. Please remember, the Wilcoxon rank sum test differs from the signed rank sum test. The steps to conduct a Wilcoxon rank sum test are as follows. First, state the hypothesis and identify the claim. Second, find the critical value using Table E in our textbook, Elementary Statistics. The third step, compute the test value. When computing the test value, we will first take all the data from both samples, arrange it in ascending order from smallest to largest, and rank each data value. Look for the smallest sample size and add up the ranks for this group. Lastly, we will plug in the values into the formulas to find the test value. These are our formulas that we will use. Our fourth step is to make the decision to reject or to accept our null hypothesis. And the fifth step, summarize our results. Okay, let's do an example. Let's pretend that a researcher is very interested in finding out who spends the most time playing the popular video game Black Ops. Is it our youth who are 17 and under, or our adults 18 and over? In order to get an idea of which age is playing Black Ops more and how often, 24 random individuals who play the game online were polled. These individuals were asked two questions. What age category do you fall into, and how much time do you spend a week playing Black Ops in hours? These are the results from the poll. Our 17 and under category, individuals said they played 7 hours. Another individual said 9. 2 more said 9. Another said 11, 12, 15, 16, 19, 21, 24, 25, and 28. And our 18 and older group, this is the hours that they said they played Black Ops a week. Let's think about our rules for conducting a Wilcoxon rank sum test, just to make sure that this example is going to work. Are our samples random? Yes, they were polled randomly. Are the sample sizes greater than or equal to 10? Yes, they are 13 and 10. Now, let's work it out. Let's start back from the beginning. Step 1, state our hypothesis. Our null hypothesis, there is no difference in the amount of time Black Ops is played between our youth and adults. Alternative hypothesis, there is a difference in the amount of time black ops is played by youth and adults. Step 2, we need to find our critical value. Since the alpha 0.05, we will go to table E to find critical values, and they are positive 1.96 and negative 1.96. We're going to continue working the example out by next arranging our data and giving it a rank. After we arrange the data in order from smallest to largest, we will add up all the ranks of the smallest sample size, which was the 18 and plus group. There's their sum for the 18 and plus group of their data, and it was 95. Next, we will fill in the formulas right here. Step 4, it's time to make the decision. Since negative 2.5 is less than negative 1.96, we will reject the null hypothesis. Step 5, summarize. There is enough evidence to support the claim that there is a difference in the amount of time black ops is played by our youth and our adults. We did it. We have now mastered the Wilcoxon rank sum test.
Hello, my name is Mary Wiggins, and today we'll be discussing the Wilcoxon signed rank test as part of our final group project for Dr. Glover's Elementary Statistics course for the fall of 2014. The Wilcoxon signed rank test is a non-parametric statistical hypothesis test used when comparing two related samples, matched samples, or repeated measurements on a single sample to assess whether their population mean ranks differ. It is a paired difference test that can be used as an alternative to the paired student's t-test, t-test for matched pairs, or the t-test for dependent samples when the population cannot be assumed to be normally distributed. The Wilcoxon signed rank test is not the same as the Wilcoxon rank sum test, although both are non-parametric and involve summation of ranks. To execute a problem using the Wilcoxon signed rank test, you must go through 5 steps. In order to illustrate this to you, I will use the following example. In a 12th grade class, a group of 6 students were tested to see if there was a difference between taking the ACT on a national test date in a room full of students compared to taking the ACT residually, or alone without any distractions. The students all took the ACT on the national test date in a room together, and then the next week they were scheduled to take the residual ACT on UT Martin's campus. Before we get into finding the solution to this example, here is a table of how each student scored on the national ACT test date and on the residual test. As you can see here, the students are labeled from A to F. After we have this data written in a table, we can go through the steps in order to determine if there is a difference in ACT scores. For step 1, we need to state the hypothesis and identify the claim. Our null hypothesis, labeled H0, states there is no difference in the ACT scores of the 12th grade students depending on whether they take the ACT with other students or take the ACT alone. Our alternative hypothesis, labeled H1, is written. There is a difference in the ACT scores of the 12th grade students depending on whether they take the ACT with other students or take the ACT alone. The alternative hypothesis is our claim in this problem. For step 2, we need to find the critical value from table K. Table K is located in the back of your book and is illustrated in the table shown on the slide. With n equals to 6 and A equals to 0.05, we can determine that our critical value is 1 as shown on the table. For step 3, we must compute the test value. This is the longest step within the Wilcoxon signed rank test, but it is relatively easy to learn. For 3A, you first create a table as shown on the slide. The next few steps we will take will gradually fill in the blank sections that you can see on this table. As you can see, the sections we have filled in are the categorization of students, the national scores, and the residual scores. For section B, we will find the differences, the national scores minus the residual ACT, denoted by XN minus XR, and place the values in the difference column. As you can see with our solutions, the differences in scores for students A through F are -1, 2, 3, 4, -2, and 1. For section C, we will find the absolute value of each difference and place the results in the absolute value column. The absolute value is the non-negative value of x without regard to its sign, so we will change all of our differences to a positive number. As shown on the slide, the absolute values of the differences are 1, 2, 3, 4, 2, and 1. For section 3D, we will need to rank each absolute value from lowest to highest and then place the rankings in the rank column. As a note, if there are absolute values that are equal in your list, you must use their ranking and add 0.5 to the value. For example, in this data set, our ranked absolute values are 1, 1, 2, 2, 3, and 4. Since two test sets of these numbers are equal to one another, our rankings will read 1.5, 1.5, 3.5, 3.5, 5, and 6. Now that we have completed these rankings, we can put this information in our rank column. For section 3E, we need to give each rank a positive or negative sign according to the sign in the difference column. According to our table, we only had two differences with a negative value, so we will change those ranks from positive to negative. From student A to F, our sign rank column will read -1.5, 3.5, 5, 6, -3.5, and 1.5. And this kind of gives you a caption of all of the different steps that we have taken in this section. For step 3F, we will section off the positive ranks and negative ranks, and we will add up their sums separately. With our positive ranks, we add 3.5 plus 5 plus 6 plus 1.5 to equal 16. For our negative ranks, we add -1.5 plus -3.5 to equal -5. As the last section of step 3 seen at the bottom of the slide, we must select the smaller of the absolute values of the sums, and we use this as the test value. In this problem, our negative rank absolute value is our task value, which is 5. For step 4, we must make the decision. In this case, we reject the null hypothesis if the test value is less than or equal to the critical value. In our specific example, 5 is greater than 1. The decision is to not reject the null hypothesis. Step 5 is here to summarize the results, and as stated below, there is not enough evidence to support the claim that there is a difference in the ACT scores of the 12th grade students depending on whether they take the ACT with other students or take it alone.
Okay, my name is Ashley Richardson, and I will be discussing the Kruskal-Wallis test. Let's look at some of the characteristics of the Kruskal-Wallis test to begin with. It is a one-way analysis of variance test. It is used when testing the null hypothesis that all populations or samples come from the same distribution, and it compares 3 or more samples by grouping data and then ranking each data set. Let's look at an example. Here's the scenario. Let's say that there has recently been a boom of automobile accidents in Haywood County. There are 4 cities in Haywood County, and they include Brownsville, Dansville, Nutbush, and Stanton. A local researcher would like to determine whether or not the total number of accidents reported over the past 3 months in the 4 different cities is the same. Now, the question is, at a significance level of 0.05, is there enough proof to reject the null hypothesis that the number of automobile accidents in the 4 cities in Haywood County are the same? Here's our data. In Brownsville, 12, 17, and 21 accidents in the past 3 months. Dansville, 8, 6, and 13. Nutbush, 15, 5, and 7. Stanton, 11, 9, and 10. To solve this equation, we will follow the following steps. Step 1. State the hypothesis and identify the claim. The null hypothesis would be there is no difference in the number of automobile accidents in the 4 cities located in Haywood County. The alternative hypothesis will be there is a difference in the number of automobile accidents in the 4 cities located in Haywood County. Step 2 to solving this equation. We will find the critical value using the chi-square table in Table G that is found in our textbook. This is what that looks like. This is Table G. In order to find the critical value using the chi-square table, we will see our degrees of freedom. The degrees of freedom formula is K minus 1. K is the number of groups. For this equation, we have 4 groups. The significance level that we'll be looking at on the table is 0.05. When we do our formula, 4, which is our groups, minus 1, it equals 3. We look at the significance level on the table, and it gives us the critical value of 7.815. Steps continued. Step 3 of solving the equation, we will find the test value. In order to find the test value, we first must arrange the data in ascending order, from smallest to largest. We will then give each value a ranking. Here are the number of accidents, and we have listed those from smallest to largest. Step 3 continued. After we list our data in ascending order, we will add up all the ranks of each group. The ranks for Nutbush include 1 plus 3 plus 10, gives us the sum of 14. The ranks for Daintsville, 2 plus 4 plus 9, giving us a sum of 15. The ranks for Brownsville, 8 plus 11 plus 12, gives us a sum of 31. And the ranks for Stanton, 5, 6, and 7, giving us a sum of 18. Now it is time to plug in the values into the Kruskal-Wallis test formula. Here is the formula right here. In the formula, N equals 9, the number in each sample added together. Since we have 3 samples, 3 plus 3 plus 3 is 9. That's where we get our N. R1 in the formula stands for 14. That is the rank for the sum of the ranks for Nutbush. R2 is 15, the sum of the ranks for Daintsville. R3 is 31, the sum of the ranks for Brownsville. And R4 is the ranks for Stanton, the sum of the ranks for Stanton, which is 18. Once we plug in the values into the formula and work out the equation, we get negative 5.352. We're almost finished. Step 4, it's time to make the decision. Since negative 5.352 is less than the critical value of 7.815, we will not reject the null hypothesis. Step 5 is time to summarize our results. There is not enough proof to reject the claim that there is no difference in the number of automobile accidents in the 4 cities located in Haywood County. We did it. This is the end of my review for the Kruskal-Wallis test. I think we are ready to try some examples on our own. Thank you.
Hi, this is Danielle Cruz. I'm in Dr. Glover's Educational Statistics class in the fall semester of 2014. We are doing the group project, and I have the assignment of Spearman's rank test. If you have ever done scatter graphs, Spearman's rank offers you the opportunity to use a statistical test to get a value which can determine the strength of the relationship between 2 sets of data. So how do we do it? As you can see in the equation, we have this stands for rho, which is the Spearman rank coefficient. It refers to the overall value or rank. Next, we know that the equation has to be done before the value is taken away from 1. Here, this means the total of. D squared is the first thing we will try to establish in our ranked tables, which is the next slide coming up. N refers to the sites or values you will process. So if there were 15 sites, N would be 15. If there were 20 pedestrian count zones, then N would be 20, and so on and so forth. The best way to do this would be through an example. If we were looking at settlement patterns for a town's central business districts and geography, we may wish to compare aspects of the town, such as whether the number of people in a zone affect the type of shops that locate there. An example, convenience shops. Here we have laid out a table of each of the 12 zones in a town. We have a column for pedestrians, as well as a column of number of convenience shops. We now need to rank the data, 2 highlighted columns. This is a shown overlay. Here you will see an example on this. The pedestrian counts have been ranked from highest to lowest, with the highest value of 70 being ranked as number 1, the lowest value 8 being ranked as number 12. So that was fairly easy. We now need to do the next column for convenience shops. But hang on, we have a problem. We have 2 variables that are the same. We have 8. So what do? The next 2 ranks would be 4 and 5. We add the 2 ranks together and divide it by 2. So these 2 ranks would now be 4.5, 4.5. As you can see, I put that in the rank column. This is probably where students make a big mistake. Having gone from 4.5, students may rank the next value as 5, but we can't. Why not, you may ask? Because we already used rank number 5, so we would need to use rank number 6. But now we have a different situation, a further complicated situation. We now have 2 more values that are the same. So we do the same again, add the 2 ranks, 7 and 6, and divide by 2 is 6.5. Having ranked both sets of data, we now need to work out the difference between the 2 ranks. To do this, we would take the second rank away from the first rank. This is demonstrated by the next slide. The difference between the 2 ranks have now been established. So what next? In this chart, you can see the difference has been established. So what do we do with these d squared figures? First, we need to add all of these figures in d squared column together. And this gives us 32. Oh, I'm sorry. Here's where we have all the d squared values and we add them, and this is what is equal to 32. My apologies. Firstly, let's remind ourselves of the equation. Rho is equal to 1 minus 6 times square sum of d squared over n cubed minus n. In this equation, we know the total of d squared, which is 32. So the top part of our equation is 6 times 32. On the bottom, we have n cubed, which we have established is 12, because remember, it's the number of sites or zones that we have, and in this case it's 12. So in this case we will have 12 times 12 times 12 minus 12. This is equal to 0.1118888111888. We are going to shorten that to an approximate sign, 0.1119. You may think we are done, but we are not. We have already established the sum. Remember, we need to take the value we just calculated away from 1. So now we have 1 minus 0.1119, which is equal to 0.888. So we now have our Spearman's rank figure, but what does it mean? Our overall value will always be between -1 in value, between -1 and +1 in value. As a rough guide, our figure of 0.888 demonstrates that there is a fairly positive relationship. It suggests that where pedestrian counts are high, there is a high number of convenience shops. Should the figure be close to -1, it would suggest a negative relationship, and that as one thing increases, the other decreases. However, just looking at a line and making an estimation isn't particularly scientific. To be more sure, we need to look in critical values table to see the level of significance and strength of the relationship. This is a shown overlead. This is a critical values table, and the N column shows you the number of sites or zones you have studied. In our case, we looked at 12 zones. If you look across, we can see there are 2 further columns, one labeled 0.05 and the other 0.01. The first, 0.05, means that if our figure exceeds the value, we can be sure that 95 times in 100 the figure occurred because a relationship exists and not because of pure chance. The second figure, 0.01, means that if our figure exceeds this example value, we can be sure that 99 times in 100 the figure has occurred because a relationship exists and did not occur by chance. In our example above, we can see that our figure of 0.888 exceeds the values at both the 95% and 99% levels. The figure is therefore highly significant. In conclusion, we can therefore conclude that this figure is strongly significant and that pedestrian counts and the number of convenience shops are clearly rated. Hi, this is Danielle Cruz. I'm in Dr. Glover's Educational Statistics Fall Semester 2014 class. We have the group project, and I'm in charge of the runs test for randomness. We're going to start out with some basic vocabulary. Runs test for randomness is used to best test claims that data have been obtained or occur randomly. A run is a sequence of similar events, items, or symbols that is followed by an event, item, or symbol that is mutually exclusive from the first event, item, or symbol. Length is the number of events, items, or symbols in the run. Runs test for randomness. Assume that we have a set of data and we wish to know whether it is random or not. Some examples are: a researcher takes a systematic sample, choosing every 10th person who passes by, and wants to check whether the gender of these people is random. A professor makes up a true-false test and wants to check that the sequence of answers is random. Runs, hits, and errors. A run is a sequence of similar events. In flipping coins, the number of heads in a row. In a series of patients, the number of female patients in a row. In a series of experiments, the number of measured value was more than 17.1 in a row. It is unlikely that the number of runs is too small or too large. This forms the basis of the runs test. Here's an example of a runs test small case. N1 is the number of events event 1 occurred. N2 is the number of events event 2 occurred. If N1 is less than or equal to 20, and N2 is less than or equal to 20, the test statistic in the runs test for randomness is R1, the number of sums. Critical values for run test for randomness. You use the table in appendix. You have the critical value alpha, which is equal to 0.05. And it is the level of significance. Large sample case. If N1 is larger than 20 or N2 is larger than 20, the test statistic in the runs test for randomness is the following formula. We have Z, which is your test statistic, is equal to R, which is the number of runs, minus mu, 1, over the standard deviation of the runs. Mu1 is equal to 2n1 times n2 divided by n plus 1. Now we have the formula sigma, which is the standard deviation of the runs, is equal to the square root of 2 times n1 times n2 times 2n1 n2 minus n divided by n squared times n minus 1. Let n represent the sample size of which there are two mutually exclusive types. Let n1 represent the number of observations of the first type. Let n2 represent the number of observations of the second type. And let R represent the number of runs. Critical values for a runs test for randomness can be found in the Table M Appendix A, the standard normal table. Example 1. The following sequence was observed when flipping a coin. You can see it's in runs. It shows you by the color of the letters. Each one is a run. The coin was flipped 16 times with 9 heads and 7 tails. There were 9 runs observed. N equals 16, N1 equals 9, N2 equals 7, and R equals 9. Critical values from the Table M Appendix A are 9, 7, and this is equal to 4, 14. Since R lies between critical values 4 and 14, then we fail to reject and conclude that we don't have enough evidence to say that it is not random. Example 2, the following sequence was observed when flipping a coin. The coin was flipped 38 times with 16 heads and 22 tails. There were 18 runs observed. Here's our values. N equals 38, N1 equals 16, N2 equals 22, R equals 18. Here's our formula that I've just went through. I'm going to work through them for you. Equals 19.5263. This equals 0.1515. Since Z is negative 0.515 is greater than negative 2A over 2, we fail to reject and conclude that we don't have enough evidence to say that it's not random.